Today we are going to study a second problem which is solved using the method of dynamic programming. This problem is called the matrix chain multiplication. The problem is that we are given a sequence of matrices that can be multiplied. So, A1, A2 up to AN are n matrices which are given, and our aim is to compute the product of these n matrices. Let us assume that the product can be performed. In other words, the orders of the matrices are appropriately given. There are many parenthesizations to compute the product. What is a parenthesization? A parenthesization is an allocation of parentheses around the expression that has been given, so that the expression can be evaluated as specified by the parenthesization. Let us now consider this example where there are 4 matrices A1, A2, A3 and A4, and the aim is to compute the product of these 4 matrices. There are 5 possible parenthesizations. Let us inspect each of these parenthesizations. This is the first one. We know that in any expression which is parenthesized, the innermost parenthesis is evaluated first. Therefore, in this parenthesization, the first one, A3 and A4 are multiplied first, the result is then multiplied with A2 and the result is then multiplied with A1. In the next parenthesization, the innermost parenthesis is the one that encloses the product A2 A3, which is computed first. The result is then multiplied with A4. The result of this matrix multiplication is then multiplied with A1. The other parenthesis, this is more interesting than the first two because it is different. Observe that there are 2 innermost parentheses. One parenthesis contains the matrix product A1 A2 and the second innermost parenthesis contains the matrix product A3 A4, and again using expression evaluation rules, the leftmost innermost parenthesis is evaluated first. Therefore, the expression involving the product A1 A2 is evaluated first, then the expression involving the product A3 A4 is evaluated, then the 2 results are multiplied, and this is given as a result of the matrix product of the 4 matrices. The following 2 are symmetric to the second and first respectively, and the explanation is similar. What distinguishes these 5 different parenthesizations? Let us just see that. What distinguishes them is the total number of multiplications. Our aim is to now count the total number of scalar multiplications which are necessary. To do this, let us understand the number of multiplications required to multiply 2 matrices. In this case, let us assume that the matrix dimensions are given. The 2 matrices are A, which is a P by Q matrix, and B, which is a Q by R matrix. We know that the result is a P by R matrix, and let us call this result matrix the matrix C. It is clear that the total number of matrix multiplications that need to be performed is PQR. It is clear that the total number of matrix multiplications that need to be performed is P multiplied by Q multiplied by R. How does this affect the behavior of chain matrix multiplication? For this, let us consider the following example where we consider 3 matrices A, B and C. A is of order 10 by 100, B is of order 100 by 5 and C is of order 5 by 50. Clearly the 3 matrices can be multiplied, that is, the product A, B, C can be computed. There are 2 ways of parenthesizing this. This is the first way where the product AB is computed first and the result is multiplied with C. Let us assume that the product AB is called D. We know that it is a 10 by 5 matrix and C is a 5 by 50 matrix. the multiplication AB takes 5000 scalar multiplications. The product BC takes 2500 scalar multiplications. Therefore, the total number of scalar multiplications is 7500. Let us consider the second parenthesization where B and C are multiplied first, followed by A. So, let the outcome of multiplying B and C be the matrix E, which is a 100 by 50 matrix. So, the product B multiplied by C, which is performed first, takes 25,000 scalar multiplications. The subsequent product of A and E takes 50,000 scalar multiplications, and therefore we can already see that the first parenthesization uses only 7500 scalar multiplications, but the second parenthesization uses 10 times more number of scalar multiplications, that is, it uses 75,000 scalar multiplications. Clearly, from an efficiency point of view, the first parenthesization is a more preferred parenthesization than the second parenthesization. This gives rise to a very interesting minimization problem. This minimization problem is called the matrix chain multiplication problem. The input to the matrix chain multiplication problem is a chain of n matrices A1, A2 to An. For every I, the ith matrix has dimension Pi minus 1 cross Pi, that is, the matrix Ai has Pi minus 1 rows and Pi columns. The first matrix A1 has P0 rows and P1 columns. The goal is to parenthesize this matrix. The goal is to parenthesize this chain A1, A2 to An, so that the total number of scalar multiplications is minimized. Recall from the previous example that different parenthesizations give rise to different number of scalar multiplications, and our aim is to choose the optimal parenthesization to minimize the total number of scalar multiplications. One natural approach is the brute force method, where we try all possible parenthesizations. I leave this as an exercise to the student to calculate how many parenthesizations are there for a chain of n matrices. It is indeed an exponential in n. The exact function is left as an exercise to the student. So, now let us use the dynamic programming approach to come up with an algorithm to find the minimum parenthesization. Let us use the dynamic programming approach to come up with an algorithm which will come up with a parenthesization that uses the minimum number of scalar multiplications. To do this, let us understand the structure of an optimal solution, which in this case is a parenthesization. For this, we need some simple notation. We use the notation A subscripted by I up to j to denote the matrix which is the result of the product Ai, Ai plus 1 and so on up to Aj. Let us now observe that in an optimal parenthesization, which we do not know, which is what our algorithm is trying to compute, in an optimal parenthesization, let k be the index where the product A1, A2 to An is split. Therefore, the approach for computing the product would first be to compute the matrices A1 k and AK plus 1 n, and then compute the product of these two matrices to get the final matrix A1 n. The key observation that we make about this whole exercise is that if we consider an optimal parenthesization of the chain A1, A2 to An, then the parenthesizations of the subchains A1, A2 to AK and AK plus 1, AK plus 2 to An will also be optimal. This is the optimal substructure. Recall that from the previous lecture, this is one of the properties of recall from the previous lecture, for dynamic programming to be used, the problem must have the optimal substructure. In other words, in this case, the optimal solution to the parenthesization contains within it the optimal solution to sub problems. So, we will verify the claim that this problem has optimal substructure while coming up with a recursive formulation of the optimum values. In this case, we again introduce a few variables which are necessary for us to compute the minimum number of scalar multiplications. So, we use the two dimensional array m I comma j to denote the minimum number of scalar multiplications necessary to compute a I j. We let m I comma j denote, let m I comma j be the minimum number of scalar multiplications necessary to compute a I j. Now, we can see that the minimum cost to compute the chain product a1 to an, recall this is a subscripted by the range 1 to n, is the value m of 1 comma n. Suppose the optimal parenthesization of a I j splits the product between a k and a k plus 1, where k is a number in the range I to j. Then we write down a recursive formulation of m of I comma j. So, the recursive formulation uses this parenthesization. The matrix a I j is obtained by the parenthesization. The matrix a I j is obtained by multiplying the matrix chain a I to a k with the result of the matrix chain a k plus 1 to a j. In other words, this is the product of the two matrices a I k multiplied by a k plus 1 j. Therefore, the total cost of computing a I j is the cost of computing a I k plus the cost of computing a k plus 1 j plus the cost of multiplying the two matrices a I k and a k plus 1 j. Note here that the cost is the total number of scalar multiplications. So, we know that the third term, the cost of multiplying a I k and a k plus 1 j, is p I minus 1 multiplied by p k multiplied by p j. This is because the order of the two matrices are p I minus 1 cross p k and p k cross p j. So, we specify the recurrence now completely, which says that the minimum number of scalar multiplications for the chain, the minimum number of scalar multiplications for multiplying the chain a I to a j is equal to m of I comma k plus m of k plus 1 comma j plus p I minus 1 multiplied by p k multiplied by p j for k between I and j. And indeed, the number of multiplications to compute an empty product is 0. That is, m of I comma I is the cost of multiplying a I, where there are no multiplication operations involved. Therefore, this is taken to be the value 0. To complete the recursive formulation, let us observe that the optimal parenthesization occurs at one of the values of k between I and j. We do not know which one it is, but the algorithmic idea is very simple. We check all the possible values of k between the range I and j and select the one that gives the least value, and this specifies completely the recursive formulation of m of I comma j. If I and j are the same, it is 0 because we do not have to perform any multiplication. If I not equal to j and I is strictly smaller than j, then m of I comma j we know stores the minimum number of scalar multiplications to multiply the chain product ai to aj. So, this is obtained by finding the best value of k by computing m of I comma k plus m of k plus 1 comma j plus pi minus 1 multiplied by pk multiplied by pj and choosing the best possible k that gives the minimum value of m of I comma j. This completes the recursive formulation of the minimum that we are interested in. Now, we need to convert this recursive formulation into an algorithm, and we have to specify the algorithm, an efficient algorithm to compute the minimum. To do this, we introduce a second two-dimensional array which we call S. S stands for split, and we refer to this two-dimensional array as the split table. The split table tells us where to split a chain. In other words, S of I comma j is that value of k at which the chain ai to aj is split for an optimal parenthesization. The steps in this algorithm are to compute the minimum number of scalar multiplications for chains of length 1. From there, we compute the minimum number of parenthesizations for chains of length 2 and 3 and so on. This is the bottom up calculation method of the optimum value of m of 1 comma n. This is the algorithm description. There is an initialization phase where the min cost table m is initialized with 0 for all the diagonal entries because they do not involve any multiplication. This is followed by 3 nested iterations to essentially implement the recurrence, and the outer loop iterates over So, let us consider this algorithmic description to compute the optimal cost. Using this data, we will then compute the optimal parenthesization also. The input to this algorithm is an array which is an n plus 1 element array which contains the dimensions of the matrices. For example, the fields p of 0 and p of 1 give us the information about the dimension of matrix A1, that is P0 cross P1. The array entries P1 and P2 tell us the dimension of the matrix A2 and so on. The result of this algorithm is we get a min cost table and a split table. These are two arrays that we get. The min cost table stores the value of the minimum cost parenthesization of the chain multiplication involving the chain of matrices ai, ai plus 1 up to aj. Similarly, the split table, the entry s of ij stores the value of the index k at which the chain ai to aj is to be split. The algorithm is as follows. It has 4 for loops. The first for loop is an initialization phase where the diagonal entries are all initialized to 0. This is natural because the diagonal entries store the value 0 to denote the fact that there is no matrix multiplication involving a single matrix. The remaining 3 for loops are nested, and the intent of these for loops is to fill the remaining entries in the upper half of the matrix is to fill the entries in the upper half of the matrix, and this is done by filling each diagonal. Observe that there are n minus 1 diagonals apart from the principal diagonal of the matrices. The outer loop iterates over the diagonals of the matrix. The outer for loop, which is indexed by the variable L, iterates over the diagonals. The next for loop is set up to instantiate each element in the appropriate diagonal, and the innermost for loop is the one that evaluates the value of the min cost parenthesization. So, in the second for loop, the initialization of the variable j to I plus L minus 1 is a choice of the appropriate element in the lth diagonal. So, m of I comma j is initialized to the value empty, which is a standard thing for a minimization problem which takes positive values. M of I comma j is initialized to the value infinity, which is a standard practice for minimization problems which take positive values. The innermost for loop is the loop that implements the recurrence that we have written to formulate the value of m of I comma j. The way this is done is to iterate over all the possible values of k starting from I to j minus 1, and the value q is computed as m of I comma k plus m of k plus 1 comma j plus p of I minus 1 multiplied by p of k multiplied by p of j. The if statement updates the value of m of I comma j if the value of q is smaller, and it also updates the value of the split entry if the value of q is smaller than the current value of m of I comma j. At the end of this whole iteration, the matrices M and S are computed, and they store the optimum parenthesization for every I comma j. They store the optimum number of scalar multiplications for the chain multiplication involving ai to aj, and the parenthesization information is stored by keeping track of the split value in the matrix S. The split table is used to compute an optimum solution. The algorithm computes first the min cost table M and the split table S, as we saw in the previous slide, and the optimum solution can be calculated from the split table using the value k which is stored in S of I comma j. This enables us to compute S of 1 comma n recursively. Thank you.